talk about certain weighted inequalities in the setting of spaces of homogeneous type. The inequalities that I'm going to talk about are for the operators such as Calderon-Zygmunt operators and some for the commutator operators. So before I go any further, I'll introduce what a weight is and talk about a little bit of motivation for our work and get to our results. So by a weight, we mean a non-negative Borel locally finite measure. The two-weight inequalities are a specialization of what I'm going to talk about, and the two-weight conjecture for the Calderon-Zygmunt operators was initially raised by Nazarov, Trail, and Wahlberg, and it was about finding the sufficient and necessary condition for the pair of weights u and v, so that the operator t is bounded from L to u to L to v. Sawyer was the one that gave a tool to kind of tackle this problem, and since it was given by Sawyer, till date we call them Sawyer testing conditions. This served as a major tool for investigation done by Nazarov, Trail, and Wahlberg. This conjecture in the special case of Hilbert transform on R was completely solved only recently when the pair of weights u and v do not share a common point mass. Since I'm talking about the Hilbert transform, and since it's the first non-positive continuous operator for which the individual two-weight problem has been solved, I'm going to introduce what the Hilbert transform is and what the result pertaining to the Hilbert operator is. So the Hilbert operator for any signed measure is defined as this principal valued integral. So if we have h, that denotes the Hilbert operator, and omega here is the signed measure, and this is the principal valued integral by which we define our Hilbert operator. The central question that was answered for the two-weight inequality of the Hilbert transform is to provide the real variable characterization for this inequality 1 that you see here, where h alpha beta is the standard truncation of the Hilbert transform. N that you see here is the best constant so that this inequality holds. U and V are the pair of weights on which we are doing this real variable characterization. In order to answer this problem for the Hilbert transform, there have been many tools like the testing condition, and one other tool that was used is the A2 condition. The A2 condition can have many different forms, and I'm going to state few of those forms to get to the theorem that was proved for the Hilbert transform. So the simple A2 condition is given for two weights u and v, such that you take the supremum over all intervals I in R, u of I over the Lebesgue measure of I times v of I over the Lebesgue measure of I. This reduces to the classical Muckenhaupt condition if we replace u dx with 1 over v of x dx. And we can also get a half Poisson A2 condition if we replace the u of I over the Lebesgue measure of I with PUI, where PUI is the Poisson integral with respect to the measure u at the scaling level of Lebesgue measure of I. The Poisson integral is defined as this integral that you see here. So here in the numerator, you have the Lebesgue measure of I, and you divide it with I plus the distance between x and I squared. Now coming to another A2 condition that we use in the statement of the main theorem is the full Poisson A2 condition, where we replace both u of I and v of I with the Poisson integrals at the scaling levels, the Lebesgue measure of I. The full solution for the two-weight inequality of the Hilbert transform is given in this theorem. This theorem is given by Michael Lacey and others. So I'm going to state what the theorem says. So this theorem says that for all x in R, if we consider two weights u and v such that they do not share a common point mass, which is given by this equation, and we define two positive constants a2 and tau as the best constants in the inequality 2 and 3 here, the theorem says that 1, which is the two-weight inequality for the Hilbert transform. So let me go back and show you what 1 is. So this is 1, which is the two-weight inequality for the Hilbert transform. So the theorem says that 1 holds if and only if both 2 and 3 hold. Now 2 is the full Poisson A2 condition, and 3 here that you see is the testing condition for the Hilbert transform. 1i that you see here is the indicator function on the interval I. Not only does this theorem give us the necessary and the sufficient condition, but it also characterizes the best constant in the two-weight inequality. It gives the best constant n in terms of the A2 condition and the testing condition. This symbol here means that there are constants c and c prime, that you can dominate this best constant with some constant times A2 power half plus tau, and you can also dominate it with some constant above by c prime times A2 power half plus tau. Now, this served as a major inspiration for our work on the space of homogeneous type. Since our work is in the setting of space of homogeneous type, I'm going to define what the space of homogeneous type is in the sense of Kaufman and Weiss and give you our result. So we say the triple x d mu is a space of homogeneous type if d is a quasi-metric on x and mu is a non-zero measure satisfying the doubling condition. Let me define what the quasi-metric on x is. A quasi-metric on x is a function that satisfies very similar properties to what a metric does on a metric space. So you have this inequality that you know for the metric space. We have the inequality where distance between x and y is 0 if and only if x equal to y. The last inequality is the quasi-triangle inequality. So the traditional triangle inequality, we put this constant a naught here in the quasi-triangle inequality, which we call the constant for the quasi-triangle inequality, and this constant lies in between 1 and infinity. Now coming to the measure that satisfies the doubling condition, we say a non-zero measure mu satisfies the doubling condition if there is a constant c mu such that for all x in the space of homogeneous type and all r greater than 0, mu measure of the ball centered at x with radius 2r can be bounded above by c mu times mu measure of the ball centered at x with radius r, and we take this to be a finite quantity. Bxr that you see here is set of all points y in the space of homogeneous type such that the distance between x and y is less than r. The r that you see here is taken to be greater than 0, and Bxr are called the quasi-metric balls in X. So now I'm going to define what a Calderon-Zygmunt operator is in the setting of space of homogeneous type. We say an operator T is a Calderon-Zygmunt operator on x d mu if T is bounded on L2 of x and has an associated kernel script kxy such that T has an integral representation in terms of this kernel. And this definition is true for all x that do not lie in the subcode of F. Along with that, we also want our kernel to satisfy the Calderon-Zygmunt kernel properties, which include the size condition and the smoothness condition. The size condition holds for all x not equal to y, where you have a bound for the absolute value of the kernel. And this bound is given as c over v of xy. I'm going to tell you in a minute what v of xy is. And we have the smoothness condition to hold for x, x prime, and y, such that the distance between x and x prime is less than or equal to 1 over 2 a naught distance between x and y. Now this is our smoothness condition that you see here. In the smoothness condition, the kappa that you see here is called the smoothness parameter. The choice of kappa can be dictated by the example that we have in our hand, but it should always lie in between 0 and 1. And Vxy that you see both in the size and the smoothness condition is mu measure of the ball centered at x with radius distance between x and y. So this is how we define a Calderon-Zygmunt operator in the sense in the setting of space of homogeneous type. The main result that we proved is inspired from the result for the Hilbert transform. However, we could only provide the sufficient conditions on the pair of weights u and v so that the two-weight inequality for a general Calderon-Zygmunt operator holds. Here, n again is the best constant so that this inequality holds. And since we were working in the generality of space of homogeneous type, sufficient conditions were the best that we could come up with. So just like we had the A2 condition for the Hilbert transform as a tool for answering the two-weight inequality for the Hilbert transform, we need a certain kind of A2 condition in our setting. So I'm going to state the A2 condition that we use in our setting of space of homogeneous type. Before I do that, a regular thing that we perform when we are dealing with space of homogeneous type, if we are using dyadic cubes, is that we split our space of homogeneous type and write it as a union of cubes that come from certain dyadic levels. And in the A2 condition, we use some of these things. So I'm going to state those terms that we use. So we take cubes Q that come from different dyadic levels that we use to break our space of homogeneous type into. And we denote by L of Q the side length of the dyadic cube that comes from the dyadic level dk for all k in Z. So when we are taking this system of dyadic cubes, we associate it with a parameter delta. Now delta is a parameter that lies in between 0 and 1. And the main assumption in our paper is that the length of the dyadic cube that comes from the dyadic level k is very similar to delta power k. So it's kind of equivalent. So that's the main assumption that we take in our paper. Now I'm going to state the A2 condition in our setting. So we say that the pair of weights u and v satisfy the A2 condition for all cubes in the dyadic level k if we have this condition. In this condition, the kqv that you see here is given by the integral, and if you observe closely, this integral looks very similar to the Poisson integral that I defined earlier. So the reason why we didn't use Poisson integral to define our A2 condition is because for certain Calvin-Zygmunt operators on the space of homogeneous type, Poisson integral might not directly, the two-weight inequality for the Poisson integral might not directly connect with the two-weight inequality for the operator. At the end of discussion for the Calvin-Zygmunt operators inequalities, I'm going to specifically give an example where this construction KQE is extremely helpful since the Poisson integral for that operator exists. However, it does not give anything related to the two-weight inequality for that operator. So the A2 condition is this condition as well as its dual condition that you see here, where I've just replaced the roles of U and V. And A2 here is the best constant so that this inequality holds. And N here is the upper dimension of the doubling measure. And we also assume the pivotal condition holds for the two-weight inequality for the general Calvin-Zygmunt operator. So I'm going to state what the pivotal condition is. For the pivotal condition, we consider a phi that is given as v of q times the new version of the Poisson integral squared. And we assume that if we take the supremum over all cubes and write these cubes as a union of some good cubes, I'm going to define what good bad decomposition is in a minute. But if we take the supremum over all of these cubes, q that come from any dyadic level, and take the sum of this function phi, we are able to dominate it with some constant nu squared times the u measure of the cube q. So this pivotal condition plays a great role in handling the degeneracies in the pair of weights we take, and it's very inspired from the original proof given by Nazarov, Trail, and Wahlberg for the Hilbert transform. So this is the statement of our main theorem. So here we say that if we consider an operator T that is a Calvin-Zygmunt operator with smoothness parameter kappa, and we consider two weights u and v that are locally finite, positive Borel measures on X, and we suppose that they do not share a common point mass, which is given by this equation. And we also assume that they satisfy the two-weight condition with the constant A2 and the pivotal condition with the constant nu. Then we say that our operator T is bounded from L to U to L to V if and only if the testing condition given by 6 and 7 hold. So the testing condition that you see here, in the testing condition that you see here, T star is the adjoint operator for the operator T. And one Q that you see here is the indicator of the cube Q. And not only our theorem gives us kind of sufficient conditions for the two-weight inequality, we are also able to characterize our best constant. So kind of give the upper bound since we have the sufficient conditions for our best constant in the two-weight inequality in terms of the A2 condition, testing condition, and the pivotal condition that play a huge role in controlling a lot of the terms. We were also able to extend our theorem to Hilbert space valued operators. So I'm going to define what a Calvin-Zygmunt operator in the Hilbert space setting is, and then give you the extended version of our theorem. So in order to define a Hilbert space valued operator, we consider two Hilbert spaces H1 and H2 and replace the scalar valued expression in the definition of singular integral with appropriate Hilbert space valued expressions. So for example, we have a kernel that goes from x cross x to bh1h2 now, where bh1h2 is the Banach space of bounded linear operators. And we have an f that goes from x to h1, which makes sure that t of f goes from x to h2. Here t is equipped with the usual operator norm. Now coming to what an h1 to h2 Calvin-Zygmunt operator is, we say that an operator T is an h1 to h2 Calvin-Zygmunt operator if the kernel satisfies the usual size and the smoothness condition. So we have the size condition given by this equation and the smoothness condition given by this equation. The smoothness condition true for all x prime and y such that this inequality holds. And along with this, we want our operator T to be bounded from the unweighted L to H1 to unweighted H to L2. Now coming to the statement of our extended version of the theorem, for that we consider two separable Hilbert spaces H1 and H2. T is a Calvin-Zygmunt operator that takes L to H1 to L to H2. U and V are two weights on the space of homogeneous type that do not share a common point mass. We suppose that the A2 and the pivotal condition both hold. Then this theorem says that if these testing conditions that you see here hold, then we are able to get the best constant to be bounded above by some constant times A2 plus tau plus nu, which are the A2 condition, the testing condition, and the pivotal condition constants. In the testing conditions that you see here, E1 and E2 are the unit vectors in H1 and H2. And the proof of theorem 2 follows immediately from the proof of the main theorem that I stated earlier. It's easier to see the proof by just considering the scalar valued singular integral operators T, E1, E2 for all the unit vectors. And we define a kernel for these operators T, E1, E2 as this inner product. And just by observing the fact that the operator norm of T from L to H1U to L to H2V is given as the supremum of all of these scalar valued singular integrals, and using the theorem 1, we end up getting the statement of theorem 2. So the proof of theorem 2. Now coming to a little bit about the strategy for our proof for showing our main theorem. As I said earlier, whenever we have a space of homogeneous type and we want to use some kind of a dyadic decomposition, we begin with certain probability space that exist on the space of homogeneous type and try to decompose our space of homogeneous type in terms of these as a union of some disjoint cubes that come from these dyadic levels. So that would be the first step whenever we consider proof using the dyadic decomposition. And the next step would be to observe some kind of a Haar decomposition for the functions that are defined on the L2 spaces of the space of homogeneous type. So even in the case that we were handling, we are able to observe that there was an explicit construction for the Haar basis given by h epsilon of q, where the epsilon goes from 1 to mq minus 1. Now this mq is the number of dyadic children of q. So if we are dealing with a traditional Euclidean setting, so if we are dealing with R, we have two children. We have the right interval and the left interval. And in the setting of space of homogeneous type, similarly, we have mq number of children. And by the works of Lacey and G, we observed that this MQ is finite, and we use that for our decomposition in our paper. And we proved that for any F that lies in the LP spaces of the space of homogeneous type, we have this Haar decomposition in terms of the Haar coefficients for F. We have also defined another non-cancellative Haar function given by h naught of q that is given here. So that is given as indicator of cube divided over mu measure of the cube to the power of half. This mu is the doubling measure that exists on the space of homogeneous type. The property of this non-cancellative Haar function is that if you take the inner product of the function with this non-cancellative Haar function, you end up getting the average on the cube that you're taking this non-cancellative Haar function to be. And it also has this property that if you sum all the Haar coefficients of cubes that are containing this cube R for which you take this non-cancellative Haar function, you end up getting this inner product or the average. Now using this non-cancellative Haar function, what we do is we consider we start the proof by looking at two test functions f and g, and we kind of write down both of these functions in terms of the Haar coefficients by considering that they have a common large support Q naught. And we kind of write down the Haar coefficients. So as you've seen earlier, we have a Haar decomposition for our function f of x. And considering that we have two test functions, now why we take this two test function is that our goal is to bound the operator norm of t. And as we have seen earlier, we can write down the operator norm of t as a supremum over the inner product of t, f, and g, where f comes from L2 of u and g comes from L2 of v. So these are the two test functions that we begin with. So instead of controlling the operator norm, we try to control this inner product. And so we begin with these two test functions f and g that come from L2 of u and L2 of v. And using the Haar decomposition for that exist on the L2 space L2 of x, we can write down f of x as the summation of the Haar coefficients. And considering a support cube, a common large support cube Q naught, we can split the Haar decomposition that we have for f into two parts where we sum over all the cubes that contain this support cube Q naught and sum over all the cubes that are contained in the support cube Q naught. Now, using the property for the non-cancellative Haar functions, one of these pieces that you see here becomes the average of the function f over Q naught, and the other piece we keep it as it is. I'm going to call the first piece here f1 and f2 so that I explain what happens in the rest of the proof. We have a similar decompositions for g1 and g2, a similar decomposition for g in terms of g1 and g2. So as I've said earlier, we start a proof by looking at the inner product T, F, and G. And now that we have a decomposition for F as F1 plus F2 and G as G1 plus G2, we can write down this inner product as this sum by using the properties of the inner product. I'm going to call each of these pieces I1, I2, I3, I4 respectively. And now I'm going to show you that the control for I1, I2, I3 is really simple. So if you look at just the term I1, which is T F1 G1, and you write down what F1 and G1 are, which are the average values of F and G on the cube Q naught, you end up getting some constant times this inner product. And this inner product of T1 Q naught, 1 Q naught is easily controlled by just using the testing conditions. So using the testing conditions, we have a control for the term I1. So the control for the terms I2 and I3 is similar. Now what this does is it makes our proof a little bit simple in the sense that for us, instead of controlling the inner product of TFG for F and G, which do not have which do not vanish, which do not have an average over the support cube Q naught to be equal to 0, we can just consider those test functions f and g for which this part is 0, since we are able to control the terms I1, I2, and I3. So it's sufficient that we look at this kind of a control for our inner product where f and g have the properties that the integral over Q naught becomes 0. We can further simplify this proof by using the good bad decomposition. So that's the next thing that I'm going to talk about. And in order to get to that, I'm going to define what a good bad cube is, and then I'm going to talk about how this good bad decomposition helps us in our proof. So for that, we'll fix a number epsilon that lies in between 0 and 1, and we consider dyadic levels given by d and d prime, where d is the dyadic system at the level k and d prime is the dyadic system at the level n. Now coming to the definition of what a good cube is, we consider a cube q in d. So q is a cube that comes from the dyadic level k. We say q is r good in d prime, where r is some large number. If for every cube q1 in d prime, such that delta power k is less than delta power r times delta power n. The delta that I'm talking here is the parameter associated with the system of dyadic cubes. And we have the assumption that length of q when it comes from the dyadic level k is equivalent to delta power k. So we say that Q is R good in D prime for an integer R if delta power k is less than delta power r times delta power n, with k greater than uh, or equal to n plus r, if one of these conditions is satisfied. So we either have the distance between q and q1 to be greater than some delta raised to some power, or we have the distance between q and x minus q1 if we have delta raised to the same power. So this is when we say that we have a good cube. If this condition is not satisfied our cube in the dyadic system, we say that it's a bad cube. Now that we have a distinction between a good and a bad cube in the system of dyadic cubes, we can actually write down our function as a good piece plus a bad piece, where the bad piece is taking the sum over all the Haar coefficients that come with the bad cubes. And this kind of a decomposition further simplifies our proof because we have the following theorem given by Reznikov that says that we have a control for the L2 norm of the bad pieces. So this is true for every function and every bad piece. So using this theorem, what we get is the following. So what this theorem does to us is it says that if we have a good and bad decompositions for our test functions f and g, and we have the pair of weights u and v, and we assume that we have a control for the inner product of t f good g good, then we end up getting the control for the inner product of TFG as a whole, which in turn gives us a control for the operator norm of T. So all our work reduces to just proving the control for the inner product of T, F good and G good instead of considering the whole function F and G in the inner product. I'm not going to prove the theorem, but I'm going to show you an extension of what happens assuming that we have that kind of theorem. So here I'm looking at the inner product T, F, and G, where now I'm considering F good and G good, and I'm just writing it down as F and G just for the sake of simplicity. So considering that I'm only working on the good pieces and using the Haar decomposition, this inner product can be written as this summation that you see here. And we can break this summation into two bits by looking at the length of the cubes that are the um, that kind of give us this Haar decomposition. So I'm considering L of Q greater than equal to L of S for one part of the summation and L of S greater than L of Q for other part of the summation. And I end up getting two pieces, which I call A11 and A12. So now in order to prove the control for my some kind of control for my in bilinear form, I can prove the control for both of these pieces. And if you observe closely, both of these pieces are symmetric to each other. So instead of working on each of them, it's okay if I just work on one of them and I show my results. So this is a flowchart of all the pieces that we get when we try to show the control. So simply A11 and A12 and computation on one of them was not easy. So we had to break our A11 into many multiple pieces and do some kind of calculations to get our main result. And this kind of is a flowchart of how A11 breaks into all of these pieces. I have a little summary about what happens in the flowchart. So the flowchart here starts at the bilinear form T FG, where I'm considering F good and G good. And the hypothesis that we use in controlling the bilinear form is either the A2 condition or the testing condition or the pivotal condition. There are certain terms in this flowchart that kind of use the stopping tree arguments, and those I'm not going to state all the technical details of the proof, but I've just numbered all the terms that use the stopping time arguments. And we have some other terms that use the paraproduct arguments. Now the proof is extremely technical and little um, large to show in this talk. So I'm going to go straight to examples and not bore you with the technicalities of the proof. So one of the example that is a major application for our proof is the two-weight inequality for the Bessel-Rees transform. Now, um, Mückenhaupt and Stein introduced a notion of conjugacy associated to the Bessel operator, uh, delta lambda, for lambda greater than 0, which is given by this function that you see here. And we define our Bessel Rees transform as this operator that you see at the bottom of the slide. And this operator is a singular integral operator on the space of homogeneous type given by R plus, that is the upper part of the real line, with the traditional metric on R, and the doubling measure that we take on this space of homogeneous type is given by d lambda of x, which is equal to x to the power of 2 lambda dx. Now, since the Rees transform is a singular integral operator on this space of homogeneous type, this becomes an application for our result, and this is a very interesting application. The reason why I specifically chose this as an application here for the talk is because there is a notion of Poisson integral related to the Bessel-Rees transform, and there have been many papers about the two-weight inequalities of the Poisson integral related to the Bessel-Rees transform. However, the Poisson integral two-weight inequalities do not relate at all to the two-weight inequality for the Bessel-Rees transform. So our version of the new Poisson integral was very important to tackle the two-weight inequality for the Bessel-Rees transform. So this is an example that kind of uses our new version of the Poisson integral, and this example kind of motivated that construction for us. Another example that could be of interest to many is the Bergman projection. So for the Bergman projection, we consider a unit ball in Cn that I'm denoting with d, and we consider the measure d mu of eta given as 1 minus eta squared to the power of a minus 1. Mu here is the Lebesgue measure on Cn, and we consider the LP space on d mu of a. This is a Lebesgue space related to the measure mu a. And we can define the Bergman projection given by TAF as this integral. So this Bergman projection becomes a singular integral on the space of homogeneous type D, where D is the unit ball, and little d here is any pseudo distance that you can take on the unit ball, and mu a is the measure that we've defined earlier. Since this is a singular integral operator on this space of homogeneous type, this again becomes an example for us. So here I want to conclude my discussion about the two-weight inequality results that we have for the Calvin-Zygmunt operator and get to our results for the commutator operators. So our work for two-weight inequalities for commutator operators is motivated by some of the work. So I'm again going to talk about a little bit of history and then give the main results in our setting. So there has been a remarkable result proved by Kaufman, Rochberg, and Weiss that talks about the commutator of Rees transform being bounded on LP of Rn if and only if the B, the commutator with which we take the Rees transform, is a symbol in the BMO space. This result was extended by Bloom for the for the commutator of the Hilbert transform, and the result he showed is kind of the second point here. For that, before I state what he proved, I'm going to talk a little bit about the setting in which he worked. So we consider P that lies in between 1 and infinity. Lambda 1 and lambda 2 are the weights that are AP weights, Mückenhaupt AP weights. He considered the weight nu that is given as lambda 1 times lambda 1 over lambda 2 to the power 1 over P. And he showed the following inequality. So in this inequality, we are kind of in this inequality, we are kind of giving a bound for the operator norm of commutator of the Hilbert operator with the function b in terms of the weighted BMO norm of the function b. So this result heavily motivated our work. And also a following result by Garcia-Correva and others kind of interested us in the maximal function to begin with. So Garcia-Correva extended the result of Bloom for the maximal commutator, where the maximal commutator is given by this function CB of f of x, which is this integral. And in this integral, we are taking the supremum over all cubes that contain the point x in Rn. And here we are dividing 1 with the Lebesgue measure of this cube. So this is the work that was done and quite inspired us to do our result in the setting of space of homogeneous types. So I'm going to talk about what we did. What we did was to provide a quantitative estimate for the two-weight commutator of maximal function Bm. The m that you see here is the Hardy-Littlewood maximal function defined in the setting of space of homogeneous type. We also obtained a quantitative estimate for the maximal commutator Cb in the setting of space of homogeneous type. So I'm going to define what Cb in the setting of space of homogeneous type is, but we kind of obtained a result. And we kind of obtained a better quantitative estimate because we worked with something called sparse operators. So I'm going to get into the details of that. Before I get into the main theorems that we proved, I'm going to state the terms that we use in our theorem since it's all very technical. So first I'm going to start with the definition of the commutator in the setting of space of homogeneous type. It doesn't really change much with from the original definition in the Euclidean setting. So we still consider a function b that is a locally integrable function on the space of homogeneous type. We consider an f that is in the LP space on X. We say this commutator bt is defined as bt of f of x is b of x times tf of x minus t of bf of x. So this definition is not very different from what you see in the Euclidean setting. Now I'm going to talk about what the Hardy-Littlewood maximal function mf of x on the space of homogeneous type is. Again, this is not very different from what you see in the Euclidean setting, except now we take the supremum over all the quasimetric balls that contain the point x. And we, instead of the Lebesgue measure of the balls, we consider the doubling measure of the balls. So we have the mu that is a doubling measure on the space of homogeneous type. And in this definition, we use mu of b instead of the Lebesgue measure of b. And in the similar fashion, like we had the definition for the maximal commutator earlier, we have a definition for maximal commutator in the setting of space of homogeneous type. And it's very similar to what we have seen earlier, except that again, here we take the supremum over all the quasimetric balls, and the measure we take this with respect to is the doubling measure on the space of homogeneous type. I'm also going to define what the weighted BMO space is in the setting of space of homogeneous type. For that, I need to define what AP weights are. So let me start with that. We say omega of x is a we consider omega of x that is a non-negative locally integrable function on the space of homogeneous type. For p lying between 1 and infinity, we say omega is an AP weight if the AP norm of omega given by this equation is finite, and A infinity, which is A infinity is considered as a union of all of these AP weights for P lying between 1 and infinity. Now that we have an omega, the definition for omega that is an A infinity weight, we can define what the weighted BMO space is in the setting of space of homogeneous type. For that, we consider omega that is an A infinity weight, and we consider B that is locally integrable function on the space of homogeneous type. And we say that this function B belongs to the weighted BMO space if the weighted BMO norm, which is given as this supremum, is finite. In this definition for the weighted BMO norm, B that you see here is the average of the function B on this quasimetric ball B. And here the supremum is taken over all the quasimetric balls, and we are dividing with the measure respect to the A infinity weight of B. Okay. Okay. Now coming to the statement of our theorem. So this theorem 4 that you see here kind of gives what we proved for the commutator of the Hardy-Littlewood maximal function. So in our setting, we consider a P that lies in between 1 and infinity. We take AP weights lambda 1 and lambda 2 and a nu that is given by lambda 1 over lambda 2 to the power of 1 over P. We suppose that we have a B that is in the weighted BMO space of X with weight nu. And we prove that there is a constant C such that the operator norm of the commutator Bm going from LP lambda 1 of x to LP lambda 2 of x is bounded above by this constant c times the AP weights of lambda 1 and lambda 2 raised to certain power multiplied with the BMO norm of B. So what this says is that if we have our function B that lies in the weighted BMO space of X, we kind of get a bound for the operator norm of the maximal operator norm of the commutator with respect to the Hardy-Littlewood maximal function. In order to prove theorem 4, we actually prove theorem 5. And the reason why we proved theorem 5 is because we observed that we can dominate the commutator of B with Hardy-Littlewood maximal function by the maximal commutator. So if we prove our result for the maximal commutator, we end up getting the proof for the operator norm of the commutator with respect to the Hardy-Littlewood maximal function. So we ended up showing 5, where we have the similar setting for P, lambda 1, lambda 2, and nu. And we ended up showing a similar bound for the operator norm of the maximal commutator. And we were also able to obtain a lower bound for the operator norm of the maximal commutator, which is given in theorem 6. So what theorem 6 says is, suppose we have a P that lies in between 1 and infinity, and we have lambda 1, lambda 2 AP weights, and we have a nu that we have defined earlier. And we consider a B that is locally integrable function on the space of homogeneous type. And we assume that the maximal commutator is bounded from LP lambda 1x to LP lambda 2 of x. Then this theorem says that our B will belong to the weighted BMO space of x with the weight nu. And we obtain a bound for the BMO norm, the weighted BMO norm of B in terms of the operator norm of CB. The strategy that we use to prove theorem 5 and theorem 4 is via sparse domination for the maximal commutator. Hence, the result, the estimate that we obtained is better than what has been already proved. So a little bit about a strategy for the proof here again. We again, since we are working in the setting of space of homogeneous type, we begin with a system of dyadic cubes on the space of homogeneous type. And we consider something called a sparse collection of cubes. So I'm going to quickly define what the sparse collection is. So we consider eta that lies in between 0 and 1, and we say a collection S in D, which is a system of dyadic cubes on X, is eta sparse if for all cubes Q in D, we have the following inequality. Now, this is not most commonly observed definition of sparse collection of cubes, but by using this definition, we obtain the equivalent definition that's more common for the sparse collection of cubes. So suppose our S satisfies this property. So the cubes in S satisfy this property, then we have an additional property that it satisfies, that for every cube Q in S, there is a measurable subset EQ in Q such that mu measure of EQ is greater than or equal to eta times mu measure of Q. And all of these EQs only have a finite overlap. Now, this is the most common definition of the sparse cubes that we know. So this is how we define our sparse collection of cubes. Once we have the sparse collection of cubes, we can define a sparse operator in the setting of space of homogeneous type by this function. So here, a sparse operator is given as the summation of fq times the indicator of q of x. Fq here is average of f on all of these cubes. And here we are summing over all cubes that come from the sparse collection of cubes. And in order to prove the bound for the maximal commutator, what we observed was we considered two sparse operator given by tau SB, and let me show you quickly. Tau star SB, which is the adjoint of this operator, and we obtained a result for both of these sparse operators. Now, showing the bounds for sparse operators is much easier than actually showing the bound for the maximal commutator. In order to show the bound for the sparse operator, we used this theorem. So this theorem says that the maximal commutator CB of f of x can be dominated from above by the sparse operator tau SB and tau star SB. So instead of directly proving our bounds for the maximal commutator, we ended up showing the bounds for operator norms of tau sp and tau star sp. The proof strategy that we used heavily relies on the properties of the sparse collection of cubes and the BMO function, and just like classical tools like Holder's inequality and reverse Holder's inequality. Okay, let me see. Okay. And in the most recent past, we have been working on giving the compactness characterization for the maximal commutator. I'm not going to get into many details, but this is the theorem that we did in the most recent past. So we kind of extended our boundedness characterization and used it to prove the compactness characterization. So for the boundedness characterization, if we want our commutator to be bounded, we showed that our function should be in the weighted BMO space. And if we want, in this theorem, what we showed was that if we want the commutator with respect to the Hardy-Littlewood maximal function to be compact, we want the function b to be in the VMO space. And I'm not, uh, I don't know if I have time, but this here is the definition of the VMO space. So in order to define the VMO space, we consider the Lipschitz functions on the space of homogeneous type, and we consider the closure of these Lipschitz functions under the norm of BMO space to construct the VMO of X. And we can characterize um, the compactness of our maximal commutator and the commutator with respect to the Hardy-Littlewood maximal function with respect to B that lies in the weighted VMO space of X. So this is where I want to stop. Thank you all for listening.